Okay, so just an update on my office hours. I changed my Tuesday office hours. I'm going to do Mondays 1 to 3 and Tuesdays 11:15 to 1. And that's, so you're getting the support for written homework will always be due on Wednesdays. If you have, but web work will be ongoing, so you can always email me questions. With web work, use the email instructor button to, let me show you that. So here's this problem here. If you're stuck on this, you need help, then don't take a screenshot and send me an email from your account. Use this button right here, email instructor, because then I get a direct link to your problem. So use the email instructor button and then give me a detailed explanation of your difficulty. Don't just say, I'm having trouble with this problem. So write something more specific. If you can send me a screenshot then of your work, that's awesome too. So give me just specifics about your difficulty. Use preview answers to get little hints and tips about the way you're answering that will save attempts. The other thing about web work, you can let web work be your calculator. You can enter expressions like 3 plus pi minus e squared times 34.83. Okay, so you don't have to put that in your handheld and then get a decimal approximation and put the decimal approximation into web work. It's actually better to do this because then you don't have to worry about how many decimal places it's going to want. This will be, if it's based on the numbers in the problem, that will be an exact answer. And then the preview answer will give you an image of exactly what you put in to make sure it's what you intended to put in. Okay, it'll have a nice image with fraction bars, and instead of trying to read it horizontally, you'll get a good image, again, an advantage to the preview button. So let web work be your calculator. You can put in long involved expressions which when computed equal the answer that you're entering, okay? Rather than putting in decimal approximations from my handheld. Questions about web work or office hours? So just I will always put on Blackboard, we'll put in the homework, I'll say, so let's do this. So always expect web work, every class, okay? And then this homework will be for outlining what's due on Wednesdays in terms of written work. And that's normally going to be what you work on in recitation. Okay, so just always expect web work. If you don't see the set posted by like 5 o'clock on the day of class for the next class, you can email me and I can say there's no web work, or yeah, I'm putting it up right now, or whatever. Okay, so just always expect web work to be due the next class, and then the written homework will be detailed in this here. Don't forget lecture videos are here, so that will start the list of the YouTube links. Questions about nuts and bolts kind of stuff? Anything? Okay, so let's work on this example. Did I start the video? Good, right? Yeah. So it says force vectors A and B are applied at the origin as shown. Find the component representation of each vector, and then find a vector that gives the resultant force at the point. So we never really talked about what's called polar form. Polar form is when you're given, like these are given, magnitude and direction. And we said that's the basic idea of a vector, that it consists of magnitude and direction. And when that's the information that you have, magnitude and say like an angle, that's called polar form. And there's also component form, where you have, say, an x component, y component, and a z component if you're in R3. So this is what this is about is we want the total force at the origin due to force A and force B. So what's that going to be? How are we going to get total force at the origin if we've got two forces pulling? Yeah, so it's just going to be adding, right? So just like you would, if we want the total force, then you're going to add it together. Well, now there's just direction involved. So visually, can you just do a quick visual sketch of what that total force would be? What would we do to get a visual? How do we add vectors? Tip to tail, right? So I could, if I want to do A plus B, I could do A, and then I'm going to take B. Remember, vectors are mobile, right? I can move this B anywhere I want as long as the magnitude and direction stay the same. It's the same vector. So I can take vector B and I can stick it up here. And that's what I want to do. Tip to tail. Something like this. And that's still vector B, even though I moved it. And then then the total, if you just want to say what's the total force at the origin due to forces A and B, then the total force at the origin is going to be the same vector, the vector from the starting point of A to the final point of B. So this is the resultant vector, or the sum of A plus B, as a rough sketch. Does it make sense? Okay, how are we going to get A plus B? How is it that we can add vectors? So we want to actually get, is the magnitude 6? No, direction is going to mess things up, right? Because 4 is in a different direction than the 2. So the magnitude of this vector is not going to be 6, right? That should be clear. So what's the key to then getting the sum of these two vectors, A plus B? On what? Except these aren't at a right, you don't have a right triangle. So remember, what is our key to adding vectors? Components, right? Components is where we can add apples to apples and oranges to oranges. So we need the component form of A and the component form of B, and then the sum is super easy, right? It's super easy. It's you're going to add the x components and the y components. So why don't you, can you, if this is 4 kilonewtons, 40 degrees above horizontal, you'll need to, how can you get the components of that? So we're going to x component, right? So think of this as x component and y component. A little shaky today, I guess it's the rain or something. Okay, so this is like x component of A, y component of A. So, and similarly, you're going to get the x and y components of B. And once you have A and B in component form, then the sum is like falling out of bed, right? Super easy. And then we want to change that back to, so we'll have component form, we want to change that back to polar form. So we want to know what, in the end, we want to know what that magnitude is. It will not be 6, right? It will be something other than 6. And maybe what angle that is. So here's the deal. You're either making progress or you're getting help, so you can work with each other. Okay, so if I didn't have a calculator, how could I express the component form of A? Jake, did you get that? If I didn't have a calculator, how could I express that?
What you could do for the first one would be, what the second piece
This, the y component?
Yeah.
Doesn't matter, sure.
2 sine of 10, or not, 4 sine of 40.
4 sine of 40. Do you guys get that? The y component of? Right, so if you've got polar form, the components are going to be using trig, sine and cosine. All right, so what, and so then the x component, so cosine 40. And then for b? Okay, negative, do I need, so, what is cosine? Oh, okay, right, so because 10 is the angle swept here, and not this angle around here, if we had the angle around from the positive x-axis, then we wouldn't need negative, right? Then the negative would be built into the cosine, right? Because it'd already be negative. But since this 10 is swept up from negative x-axis, we need to throw that negative in there, right? Negative, what? 2 cosine 10. Everyone see that? What angle is that from positive x? 170. So I could do positive 2 cosine 170. That also works. Both work.
Which is just like one way to think about it.
Well, because normally our angles are swept counterclockwise from the x-axis. So if you just, and then that way you don't have to worry about positives and negatives. They'll always work themselves out. But this is fine too, negative 2 cosine. And then what's the y component? 2 sine 10. All right, so then a plus b. Anybody have, do all the math, right? So we're just going to add x components, add y components. Who's got the x component? Someone else get that? Good. And then y component? 2.92? Are we in agreement? Okay. So then what's the total magnitude of force at the origin? What would you do? Take the magnitude. So the magnitude of force would just be the magnitude of that a plus b vector. So I could write it this way. Anyone got that? Nice nod. Anyone else get that? 3.12 kilonewtons. Notice, very different from 6. And why is it so much less than 6? What's happening here that makes it so much less than 6? The x components have a canceling effect, right? So the part of A pulling to the right and part of B pulling to the left kind of cancel out. So that's why this is going to be much less than 6. And then the y components are just going to add together. And then the total magnitude of that is 3.12. If we wanted to get that angle then, what would we do? Inverse tangent, right? So it's going to be the y component divided by the x component, inverse tangent, right? Because the tangent of your angle is your opposite over adjacent, and this is like your opposite side and your adjacent side. So get that ratio of opposite over adjacent. Inverse tangent will get the angle. Questions on this example? Okay, so let's go back to R3. So we're going to live a lot of our life here in this course in R3. First thing, so just a quick thing I want to talk about. So just like the quadrants were named by the angle, right? So by our trig angle that sweeps counterclockwise from the x-axis around counterclockwise, we get the quadrants 1, 2, 3, 4 like this. So in space, the coordinate planes, so we've got what? We've got the xz plane, the yz plane, and the xy plane break up space into 8 octants. Okay? And so the 8 octants will follow this same pattern. The first 4 octants are for z greater than 0, so above the horizontal xy plane, and they're just the same as this. So our first octant up here, where all x, y, z are positive, is 1. And then we're going to, so imagine the same thing. Imagine the same angle theta, right? Going counterclockwise around. So octant 1 is right in front of us, right there. Octave 2 is back up here. Octave 3, octant here. Octant 4 over here, just like these. And then octaves 5 through 8 are exactly the same, but for z negative. So octant 5 down here. Octant 6 down below back here. Octant 7 Wade back down over there, and octant 8 bottom over here. But usually the only thing we refer to is the first octant usually. First octant is where all are positive, right? So your x value is positive, your y value is positive, your z value is positive. So this is the one that's kind of closest to us as we're looking at it, right? It's kind of like the octant we're in when we're looking at this. You see that? That's the first octant. But then the second, third, and fourth match the same thing with x, y, and z, based on the counterclockwise angle from the positive x-axis. Does it make sense? Okay. So remember we said vectors are mobile. Vectors are mobile. And so there's kind of a special position for any particular vector is when you put its tail at the origin. So when you put its tail at the origin, that's called standard position. Or it's a standard position vector. And then, so this is I'm showing you the vector here, 2, 3, 4. The red vector is 2, 3, 4. Okay? And what vector is the tip, or what octant is the tip in for 2, 3, 4? First octant, right? All x, y, and z are all positive. So this box that I've drawn to see it this box is in octant, the first octant. Okay? That's all I should have showed you, right? First octant, second octant, third octant back there, fourth octant over here. So did I say that was 2, 3, 4? 2, 3, 4. Okay, so this is standard position of this vector. Of course, that vector is mobile if you put its tail somewhere else. As long as it has the same direction and the same magnitude, it's the same vector, right? But when you put that tail at the origin, that's kind of a special place for it, right? So it's called the standard position vector. And when you do that, what happens? The point of the tip. What's special about that? The components, right? So if this is the vector, what did I say, 2, 3, 4? And then you put that vector in standard position, then what are the coordinates of the point of the tip? 2, 3, 4. Because why? Because the change of x and the change in y and the change of z from the origin gets you to that location, right? So now the changes are the same as your location. That's only true if the vector is placed in standard position. Okay, questions on that? So, random thoughts today, random thoughts. Okay, so now I want you to find, if this is, again, this is 2, 3, 4. Can you find the distance here's a point right there. That's at the midpoint of that segment. Can you find the distance from that point to that point? What would the distance be from that point to that point if this is the vector 2, 3? I just changed point B. Okay? Slightly more interesting. All right, so from point A to point B, I want to know what that distance is. Check with the person next to you or get help if you're stuck. But I want you to find vector AB and the distance from A to B. Paul, did you finish?
I did.
Okay, Paul, talk to me. What'd you do?
So I found the vector by subtracting the point B from point A, the coordinates of the z.
Okay.
So that would be vector 1, -3, 4.
So 1.
So 1.
What does 1 mean?
The 1 is the increase in the x direction.
Okay. All right. So the change. So you get the change in x of 1. Okay.
And the change in y of -3, so it's back -3.
Okay.
And the change in z of 4, because it goes up 4.
So you really that's vector AB.
Yes.
Okay.
And I just took the magnitude.
All right. So that 1 comes from what? X final minus x initial, and then y final minus y initial, z final minus z initial. Everyone good on vector AAB? Does this make sense? All right. And so then you said you just took the magnitude. So how do you do that?
So I squared each of the components and then added them and took the square root. So 1 plus 9 plus 16 is 26. The square root is 226.
So let's just. And so notice that that's just what? That's just the distance formula, right? And the distance formula is just based on Pythagorean theorem. So now it's like kind of a two-part Pythagorean theorem. You take Pythagorean theorem kind of in a plane parallel to one of our other planes, and then do it again, and you kind of do the Pythagorean theorem twice. And when you do the Pythagorean theorem twice, you get the distance formula in R3. Which is just 1 squared plus -3 squared. And what is that? Square root of 26? Okay, so in R3 then, getting the magnitude of a vector is just the same as in R2, but now you have one more coordinate. So you just got one more coordinate, or actually change, one more change, right? The z change. You're going to square that and add that under your square root. Again, this is based on the distance formula, which just comes from kind of Pythagorean theorem twice, right? You're going to do Pythagorean theorem twice. Any questions on that?
Yeah,
please.
Can you go through those components again about how the final minus initial, just kind of piece by piece?
So what did you get? What did you get for the coordinates of B?
Yeah, I didn't. So because I don't understand the x, y, z so much, so that's why.
Okay, so this is our x-axis, and this is our y-axis, and this is our z up. And so these points were based on the box from this original vector 2, 3, 4, right? So what is the x-coordinate of that point, right? The x-coordinate is the same as the x-coordinate of our, because you're coming out, what, 2? Do you see that? And then what about the y-coordinate of this point? It's 0. You're not going to, right? Because you're not taking the y-coordinate of 3 like you did in this one, so it's just 0. And then what's the z-coordinate? Same as the z-coordinate of that, right? Because it's the 4 up. So you're going to do the 2 for x and the 4 for z, but no y. So you get 2, 0, 4. Is it better? And so then a, the only thing for a then is it's going to be half. So I said that was the midpoint. It's going to be half of x, which is 1. Y is R3, and z is 0. So that answer it? Cool. Yeah?
Could you show how basically like taking the Pythagorean, using the Pythagorean theorem twice, like gets you that formula?
Let's do it later. How about that?
Okay.
It takes a little time.
Oh.
But basically, you do it so you. So here's the right triangle. But to get this leg, you need a Pythagorean theorem also. You see that? So we know that's going to be our what, 4 squared? But then this is the Pythagorean theorem on this triangle, which is our what? 1 squared plus 3 squared. Do you see it? So that Pythagorean theorem gives you that leg, and then that leg with that one gives you the whole leg. That was faster than I thought. Other questions? Okay, so then how about I want the set of all points that are 2 away from that point. So we've got our distance formula now. Use the distance formula to express all points that are a distance of 2 away from this point. Call this point Z. No, not Z. C. So I want express all points in R3 that are a distance of 2 away from point C. Can you do that? Nope, all points in R3. So all points two units from C. And so when you're talking about all points, so they're just a couple, or how? So just in general, how do you express when you say you're expressing all points? How do you do that? But just in general, if all points, right? I'm expressing all points. What? How do I represent that symbolically? Nope. No. So we need like all points would be like you need like an arbitrary point, right, to express all points. So what's an arbitrary point in R3? You know what arbitrary means? Not specific, right? Not specific. So it's going to represent all points. So what would I write? 0 is very specific. X, Y, Z. Right? So then that can take on whatever all points we're talking about, right? Can you do it now? So we can express all points. In other words, all ordered triples X, Y, Z that are 2 units from C. Here's the hint, right? What does 2 units from C mean? It means a distance, right? Distance. Here's another hint. C is 230. You got everything you need, right? You've got 2 points, you've got a distance. Let's spin the wheel. Spin the wheel. Where's Joseph? Joseph M.
That's me, but I don't know how to do it.
Okay. How do you find the distance in R3?
Distance in R3, x squared plus y squared plus z squared. No, that's magnitude.
Yeah. So distance between 2 points. Do you know?
Final minus initial.
Okay, that's part of it. So, Caitlin, did you get it? Yeah, but you don't have to reinvent the wheel, right? You don't have to reinvent the wheel. We're doing distance. So how do we find distance between 2 points? Griffin.
I'm just gonna give it a shot.
Okay.
Is it square root of 2 equals x minus 2 squared plus y minus 3 squared plus z squared?
So x minus 2 squared plus y minus 3 squared plus z squared, and then square root equals distance, right? Distance in R, we just did it, right? Distance in R3. So that equation that equation means all points that make that equation true are going to be all the points that are 2 away from C. So square roots are not convenient. How can we get rid of the square root? Just square both sides, right? And if we square both sides, we get equals 4. So here's maybe a little friendlier version, right? Friendlier version of that. So all XYZ triples that make that thing true are going to be these points that we want, the ones that are 2 away. If it doesn't make that equation true, it won't be two units away from C. So let's put that in and see what we get. What are all points? Many of you already know, but what are all points 2 away from point C? So x minus 2 squared plus y minus 3 squared plus z squared equals 4. Use transparency. What's it going to be? Sphere, right? And so if it's all points 2 units away from C, what point should it go through? Do you see which point it should go through? In the box? Well, yeah, no, C is the center. It's not going to go through C. C is the center, so it won't go through C. It's going to go through that point, right? See that right there? It should. Does it? Yeah. Because that's 2 units away. That point on the box right there, what is it? 0, 3, 0. That's 2 away from C. Okay, so this is, when you talk about all points a certain distance from another point, in R3, that's a sphere. And this is our equation of the sphere. So 4 represents what about the sphere? Is it the radius? Radius squared, right? It's the radius squared. And so then all points, x, y, and z, and then oftentimes we'll use a, b, c to mean the center. So x minus a squared, y minus b squared, z minus c squared equals r squared is the equation, general equation for a sphere centered at ABC with radius r. So questions, does it make sense? Does it make sense? Any questions on what we did, how we did it, what it means? All right, so then there comes this kind of thing that you need to know how to do. Let's do something fast. So oops. All right, so say we had, x squared plus x plus y squared minus 9y plus z squared plus 8z equals 0. So what you have to see is that that is also a sphere. That's also a sphere. It's just not in this tidy form based on the distance formula. So to change that into this form, so this is the form we want, right? Why? Because we can just look at that form and know the center and the radius, right? Just look at that form, we know we can pick off the center, pick off the radius. So to get it into that form, the thing about this form is you have perfect squares, right? You have perfect squares around the x, y, and z. So you have to complete each of these squares. So let's just get rid of the 9y. Let's just do that. So x squared plus y squared plus z squared plus 8z equals 0. So to complete the square, what you do is you take half of the coefficient of the linear term and you square it. half of the coefficient of your linear term and you square it, and that completes the square. So what's half of 1 squared? 1/4. So when I do x squared plus x plus 1/4, now that thing is a perfect square. What is it? X plus 1/2 squared. Did you see what happened? So by adding the 1/4 in there, I got it to be this perfect x plus 1/2 squared. And then what about y squared? If there's no linear term, then you know, you're golden. Just leave it. It's easy. And now this one, you're going to add 16. All right. So, but what did I do? I just added a half, a fourth, and I added 16. Therefore, I need to add those on the other side too to keep the balance, right? So I can't just change one side of an equation. I got to change both. So 16 and a fourth is what, 65 fourths? So we get x plus 1/2 squared plus y squared plus z plus 4 squared equals 65 fourths. So this original equation was the sphere with radius what? Square root of 65 over 2 is the radius of this circle, sphere, which is the same as the sphere. And the center is? Careful. -1/2, 0, -4 is the center of that sphere. So, and this is the radius. Radius is square root of 65 over 2. Did you catch it? Does it make sense? So this is just kind of algebra, right? So spheres, they can be in different forms as long as they have this, all the positive, when you have x squared and y squared and z squared, they're all positive on the same side. Then you'll have a sphere. And you can complete the square and find the center and the radius. Okay, messy screen, but hopefully your notes are neat and organized. Okay, I'm going to quickly start this. Questions on spheres or distance in space? All right, just wait a second before starting this. Actually, change that. You take that. All right, and then when they get to this side, if they run out, then you got to pass up and down, okay? Questions about spheres? Okay, next thing, random thoughts. So we've seen multiplication. So multiplication, we've seen one kind of multiplication, and that was scalar multiplication. And what was scalar multiplication of vectors? Yeah, it's just a scalar times a vector, and that, what does that do? That don't look at the sheet yet. Don't get distracted. Listen. Scalar multiplication is when you scale a vector to a new magnitude. What about the direction? Same, except if your scale is negative, it'll be the opposite direction. So it's still going to be a parallel vector, right? You're going to scale a vector to a new magnitude. New vector will always be parallel. It may be the same direction, maybe the opposite direction. But the idea of scalar multiplication is well phrased, right? Because you're scaling the old vector by some amount. You're like magnifying it or shrinking it and keeping it virtually in the same direction. It might be in the opposite direction. Okay, so another kind of multiplication is what's called the dot product. There are actually three kinds of multiplication relative to vectors. Scalar multiplication, we got down. It's the easiest one. Dot product, I'm going to give you the algorithm, and then this worksheet is going to help you figure out what it's all about. So the algorithm for dot product is this. Say x1, y2, y1, dot x2, y2. So this is what? Two arbitrary vectors, R2 vectors. If you multiply those with a dot product, what you get is a scalar x1 times x2 plus y1 times y2. So what do? You multiply the corresponding components, and then you add. So what will it be in R3? Then you'll also have plus z1 times z2 in R3. You'll always have that third term. So what happens? When you do a dot product, you're multiplying two vectors together, and you get a scalar. Notice, this is important. What about scalar multiplication? You multiply what two things together? You multiply a scalar and a vector, and you get a vector. You get a scaled version of the original vector. Dot product, you multiply two vectors together, vector 1, vector 2, and your result is just a number. Okay? And so this worksheet, did everyone get one? Are there any extras? This worksheet is to help us discover what the heck the scalar is about. Given the two original vectors, right, they could have any direction or magnitude, you get this number in the end. What does that number mean for the original two vectors? That's what we want to figure out. Now we have a minute. So let's just look at the first row up there. So, so what I want you to do is, this will just be a little, very quick thing you can do for Friday. So we want to draw both those vectors. So let's do the second one. Second one in the top row. So always has standard position vectors. So you're going to sketch all these vectors as standard position vectors. Sketch 5, 0 and 4, 3 as standard position vectors. And then according to this algorithm that I gave you, what is the dot product of 5, 0, dot 4, 3? What would it be? It would be 5 times 4 plus 0 times 3, which is 20. So you put 20 in the box. So you draw both the vectors as in standard position, and then you fill in what's in the box. So, let's see. So you can think about this or not, but what I want you to do for Friday is just come to class with this whole sheet finished. And it can be a totally mindless exercise if you want, and we'll start thinking about it Friday if you want. So that means do what you just did in that box for every box on this page. Draw them both as standard position vectors, write the dot product in the box, and bring that first thing Friday.